Hello, everybody. Welcome back. I hope you'll be happy to know that we're getting towards the end of this topic now of atomic physics and radioactivity. There's just a couple of little things left on the syllabus. One of them is what we'll cover today. I don't know why, but Cambridge have left this tiny little topic on the syllabus that doesn't really connect with anything else, and they say it's important that you understand how different types of radioactivity move through different types of fields. Okay, before we move on, it's worth talking about what a field is. In physics, a field is just a place or an area or a volume in space where one physical quantity affects something else. So it could be something like a gravitational field. So it's an area or a volume where gravity affects other things. It could be force field, where forces affect other things. It could be an electric field where electric charge affects other things. It could be magnetism, a magnetic field, and so on. Now, Cambridge says, luckily for us, there's only two types of field we need to cover today, which are electric fields, which are created by positive and negative charge, and magnetic fields, which obviously are caused by the north and south poles of a magnet. And the other thing that Cambridge says is that we only need to talk about alpha particles, beta particles, and gamma radiation, and if they're inside a field, how the movement is affected. Okay, so I think you'll find electric fields very straightforward, and I think you'll find magnetic fields fairly complicated. One reason for that is we've not covered electricity and magnetism yet, and those fields are part of that topic. So I'm going to try and explain this without going into too much detail because we'll go into the detail later. If you really think I've not explained it very well, please just get back to me and we'll go through it in a bit more detail. Okay, so this diagram represents an electric field. An electric field is very easily created. If you take two metal plates parallel to each other, like you can see in the diagram, like that, and if you give one of the plates a positive charge and one of the plates a negative charge, the space between them will be a field, an electric field or electrostatic field. Very easy to do that, by the way. All you need to do is connect a wire between them and connect a battery between the two wires. A battery or a cell is just a device that moves electrons around. So basically what it's done here, I don't know if you can see that, the top plate has a positive charge, so we've moved electrons away, and the bottom plate has a negative charge, so we've given it more electrons. Top plate, less electrons, bottom plate, more electrons, and the space between them therefore is an electric field. Right, so I'll try and do this fairly quickly because I think it is fairly straightforward. If I start with a source of alpha particles over here, and it's going to fire alpha particles in one direction and they're going to move from the left of the screen to the right of the screen. The question is, how are they going to move? Are they going to go straight through in a straight line? Will they bend up, down, left or right? What will happen to their movement? Okay, so here all you've got to remember is an alpha particle is positive. It's got a positive charge, and you might have already figured this out. As it fires through, or as a beam of these things go through, or a stream, as they go through in this direction, they are going to be attracted to the negative plate and repelled by the positive plate. So therefore, as the alpha particles move through, you'd expect them to bend downwards uniformly, because it's a uniform field. We've got just as many positive charges up here as negative charges down there. So we expect, in this case, because I've got my positive plate at the top and negative at the bottom, it will bend downwards towards the negative plate. Let's try and move on fairly quickly. Beta, you might have already figured this out. A beta particle, a stream of beta particles are electrons, and they are negative. So again, we're going to fire the beta particles in a stream through the two plates, and as they move through the plates, because beta is negative, it's going to be repelled by the negative plate and attracted by the positive plate. Like charges repel, negative, negative, and opposite charges attract, positive, negative. So in this case, the stream of beta particles will bend as they go upwards towards the, should be now, towards the positive plate. Terrible diagram, but I think you get the gist. The good news is gamma is very straightforward. Gamma has no charge at all. It's not a particle. It doesn't have any electrons or protons inside it. It's just a stream of energy, or a ray of energy. So the gamma ray won't be attracted or repelled by either plate. It will just move straight through the two plates in a straight line. That is supposed to be a straight line. Okay, I hope that made sense. We'll move on to the slightly more difficult term now, the section now, which is magnetism. This might take a little bit of explaining. I'm quite pleased with this diagram that I've done. It's a picture of my left hand. Hopefully that will become obvious while I've done that in a minute. Okay, so we're going to do the same thing again here. In this case, we don't have positive plate and a negative plate. We have a north pole of a magnet and a south pole of a magnet. And just like with the electric field, between these two poles we have a field, but in this case it's a magnetic field. What you need to know for this point, at this point, is that magnetic field is always in the direction of north to south. So in my diagram, the magnetic field is from here to here, from north to south. Okay, on the right of the screen I've got a little diagram of my left hand. So I'd like everybody, please hold up your left hand like you see it in the diagram. A bit like a toy gun. All of your fingers should be at 90 degrees to each other, including your thumb. 90 degrees to each other like that. You can see that. Okay. This little model was named after John Ambrose Fleming, famous Scottish physicist. And he realised that these things are all at right angles to each other. Your first finger represents the direction of the field, magnetic field. Your second finger represents the movement of particles, we call it current. And your thumb represents the way they're going to be deflected. Okay, right, so let's try the same thing again. I think I started with alpha before and I did it in red. Okay, so here's my source of alpha particles, and we'll fire positive. I'm going to fire them again from the left of the screen to the right of the screen, but in this case through the magnetic field. Okay, so to do this we're going to use Fleming's left hand rule. It's got to be your left hand, by the way, not your right hand. Okay, so current is the movement of positive charge. Current is always the movement of in the direction of positive charge moving. Because alpha is positive, that means your current is going to be moving in this direction from the left of your screen to the right of the screen. The question is how it's going to bend. Okay, so your second finger represents current, so it's going to be in the direction that the alpha particle is moving. Your first finger represents the field, so you need to point. Move back a bit. You need to point your, without breaking your wrist, point your first finger down. Point your second finger in the direction of the alpha particles, and you should see that your thumb is pointing into the screen. So what that means is, as the alpha particles move through the magnetic field, they're going to move away from you into your computer screen. Does that make sense? In this kind of direction. Moving through, then bending in that direction. Now, I hope that made sense. You might have to stop the video, rewind and go through it again. But I'll move on. Okay, here's beta. Beta, you know, is negative. I'll fire it again in the same direction. Okay, that's where it gets a bit tricky. Because beta is negative, movement of negative charge, that's the opposite of the movement of positive charge. So therefore, if your beta particles are moving in this direction across the screen, we would say the current is moving in the opposite direction. If that's not clear, just remember the current is always in the same direction as the alpha particle, but in the opposite direction of the beta particle. Left hand again. Field again is down. Beta particles are moving left to right, so the current is moving from right to left. And you should see that your thumb, like mine, is now pointing towards you. So the beta particle is going to move across the screen in this direction and then bend towards you, towards your face. Hope that made sense. Okay, and then finally, the good news is gamma again is very straightforward. Gamma has no charge, and therefore there's no current created. So therefore, gamma, it's moving from left to right through the field. It won't be affected by the field. It will just carry on straight through, as it did in electric field. Okay, so it's difficult for me to show this in 2 dimensions on the screen. The alpha particle from left to right and moves into your screen. Beta particle is moving from left to right and then moves towards your face. Gamma ray, straight across. It won't be deflected by the magnetic field. Okay. Hope that made sense, but as I said before, get in touch with me if you'd like me to go through it and maybe look for some better 3-dimensional models of how that works. Just before I wind up, you might see a magnetic field represented like this. So in my first diagram I had the North Pole at the top, South Pole at the bottom. It could have been flipped any direction, left and right, up or down. This is a way that Cambridge might show you a field. In this case, the field, the cross it's not a plus, it's a cross. It represents a magnetic field that's going into your screen. In other words, the North Pole of the magnet is in front of your screen and the South Pole of the magnet is behind your screen. Have a think, if I put, let's make it a little bit more complicated. If I put alpha particles here, and I fire them in that direction, how do you think they would deflect? The same with beta. In that direction, through the field, how would they deflect? Hopefully it's fairly obvious what would happen to the gamma rays. Okay, give that a go before you try the questions that I'm going to attach to this this video when I upload it for you. Okay, I found that quite difficult to explain, and I probably didn't do a very good job of it. But see what you think. Try the questions, and if you can't do it, please just drop me a mail or drop me a comment on the Google Classroom, and I'll try and explain a bit better. All right, thanks very much, everybody. As usual, take care. Take care of your family, and as I always say, well, I don't know when. Hopefully, we'll bump into each other soon again. Okay, goodbye.